In this video, we're going to learn about the Fisher-Irwin test. The first thing that I'll tell you about the Fisher-Irwin test is it's usually known as Fisher's exact test. If you were to do some browsing on the web under Fisher's exact test, you would in fact come up with the Fisher-Irwin test. So why do I call it the Fisher-Irwin test? In part because it was independently developed by Fisher and Irwin right around the same time period. But another reason that I like to call it the Fisher-Irwin test is because Fisher's exact method, as you have seen in previous videos, can be applied to a whole host of tests. So I don't think that calling it Fisher's exact test is very descriptive. Nonetheless, if you are getting an article published, you probably are going to need to call it Fisher's exact test, or you can call it the Fisher-Irwin test and mention, as I have done here, that many people call this Fisher's exact test. Here's the setup. We have two independent samples, just like we had when we looked at the product binomial. We have independent observations within our samples. We have a dichotomous response variable, and the number of successes is fixed for each sample. Now there's a couple points I need to make here. First of all, let's start with that last bullet, the number of successes fixed for each sample. Why would it be that we know in advance how many successes we're going to have? Well, I'm going to provide you two examples that I think are reasonable examples of when you might know in advance the number of successes. In one of the examples, we're going to have a fixed number of slots to be filled, and therefore you can't have more successes than you have slots to be filled. And in the second example, we're going to look at a special case of the Fisher-Irwin test, and that is a test for the difference in two medians. The other thing I want to point out here is that in the second bullet, I put independent observations in quotes. Why do I do that? Well, we should make our observations independent of each other. However, there's a natural dependency that arises because of the fixed number of slots or the fixed number of successes. If we know what the total number of successes are going to be, then we have limited our degrees of freedom, and we create an inherent dependency. For example, suppose we have 5 slots and we've already filled them. Then the next observation, even though we make it independently of the other observations, we know the outcome in advance. It's going to be a failure. And so that's why I have independent observations in quotes. We should indeed carry out the study looking at every individual and every participant independent of the others, but there's going to be a natural dependency that arises. This means we cannot use the product binomial in order to calculate probabilities of outcomes. We have to use the hypergeometric formula. This is used to calculate the probability of observing a specific value of delta hat. Note we're still using delta hat, the difference in proportions, even though the setup's a bit different because we have a fixed number of successes. Because we have a fixed number of successes, both margins of a 2x2 contingency table are fixed in advance. We know not only each of the sample sizes, but we know how many successes we'll have and how many failures we'll have. What we don't know is where the successes will occur. We can put what happens in our sample observations into delta hat, which also serves as an estimate of what delta is in the population. The samples are independent of each other, and the observations within samples, as I've discussed, are made independently. So here is the formula for probability. Notice it's not the product of two binomials. This is the hypergeometric formula. N1 represents the sample size for sample 1. X1 represents the number of successes in sample 1. N2 is the sample size for sample 2. X2 is the number of successes in sample 2. Then N represents the total sample size across the two samples, summing them together. and X is similarly the total number of successes that you have in your study. So N1 choose X1 times N2 choose X2, all divided by N choose X, provides the probability of a particular delta hat under the null hypothesis that delta equals 0. Let's look at an example. We previously analyzed data obtained from 2 samples created by randomizing 20 band students to morning and afternoon tryouts for the all-state band. Let's again consider this scenario, but this time suppose that these students all come from one school. The All-State Band Committee has indicated how many students can be accepted from each school based on school size. For this school, there's only 5 slots that can be filled by band members from the school. So in this particular state, they're taking precautions that we don't have an overwhelming number of all-state band members coming from one school, perhaps that has a terrific music program. Here we have again randomized participants to 2 conditions. This time the 20 participants are from one school, 10 of them for the morning, 10 for the afternoon, just like we did in a previous video. What's different now is that we not only know that it's going to be 10 and 10 in our row margin, but we also know in our column margins that it's going to be 15 and 5. That is 15 failures and 5 successes. Those row and column margins are both known in advance. That's why we have to use the hypergeometric formula. In this case, notice that we have 40% success or 4 successes in the morning and 10% success or 1 success in the afternoon. So the difference in proportions, our delta hat, is going to be 0.3, positive 0.3 if I subtract afternoon from morning, and negative 0.3 if I subtract morning from afternoon. Now let's take a look at how we can use the hypergeometric formula to create a hypergeometric distribution. Consider all possible outcomes given the fixed margins. In order to do that, you only need to focus on one cell. That is, we only have 1 degree of freedom. For example, suppose I have 5 successes in the morning. I automatically know that I have no successes in the afternoon. I know that I have 5 failures in the morning, and I know that I have 10 failures in the afternoon. Setting just that one cell told us what all the other cells would be, and therefore tells us what delta hat will be. So if you look here, I have listed down here the morning successes in a column and the afternoon successes in a column. And then I calculated delta hat, this column, by taking the morning success proportion and subtracting from it the afternoon success proportion. For each of these, based upon the 4 values in my table, I can calculate the probability using the hypergeometric formula, and that's what we've done here. So this is, as with all probability distributions, all possible outcomes, and the probability is calculated for each. If we summed up these probabilities, we would see that it sums to 1. Note that I used an R function, d hyper, in order to calculate the hypergeometric probability. Here I've done it for the one situation that we actually observed, in which we have 4 successes out of 10 in the morning, we have 10 in the other sample, and we have a total of 5 successes. Using the same function for all the possibilities that I've listed down here is how I came up with these various probabilities. So how do we find a p-statistic? We do so in the usual manner, that is, we look at what we actually observe and then look at values that are what we observe and more different than the null hypothesis than even what we observed. So if you're doing a 2-sided test, you look at the absolute value of delta. So looking back here at our distribution, my value of delta was 0.3, so I need to look at 0.3 and higher on one end and negative 0.3 and lower on the other end. And if I add those together, I get 0.30. If I wanted to do a one-sided hypothesis, say I suspected that the judges are biased toward the morning performances, then I can just add up the probabilities for delta hat being greater than or equal to 0.3. So looking back at our table again, I would only look at this upper tail of probabilities. We have an R function to do that, and that is the Fisher.test function. Fisher.test is part of base R. So here I'm going to enter my outcome table right into this function, one easy command in which I give it the table of outcomes. And you'll notice that we ended up with a p-value of 0.3034 here, which is exactly what we found a moment ago for the two-sided test. And down here for the one-sided test, 0.1517. If we look back, there's my 0.1517, there's my 0.30. So I'm just showing you here that the function does, as we would expect, exactly what we would do if we did this by hand. Now, a word about the odds ratios here. First of all, whether or not you get odds ratios above or below 1 are going to depend upon how you arranged your table. But what I wanted to particularly point out, that in past videos I've shown you how to create an odds ratio based upon our observed frequencies. In reality, technically, odds ratios are created by taking ratios of probabilities, not frequencies. It's just that if you have independence of all your observations, then using the frequencies gives you the same thing as if you used proportions or probabilities to calculate the odds ratio. So when I did it before, I did it with frequencies, and it was correct because we had total independence. Here, as I've explained, we don't have total independence. We're not going to go into calculating the probabilities for each of our cells, but if you were to use the frequencies to calculate the odds ratio, you'll get a little bit different answer. Not much, but a little bit different answer than what you see right here of 0.18, and that's because of the dependency. The function is handling that for us. So you can believe the odds ratio function, not your hand calculation, if you're doing your hand calculation based upon the frequencies. Now let's look at a special case of the Fisher-Irwin test, and that is a test for median equality. When the response variable for a single sample yields quantitative data, you know from past videos that we can use the sign test as a test of a hypothesis about the median. In a similar fashion, we can use the Fisher-Irwin test as a test of a hypothesis about the equality of two medians. So it's like using the Fisher-Irwin test as an extension of the sign test. What we did with one sample with the sign test, we can do with two samples with the Fisher-Irwin test. Let's look at an example. An independent evaluation firm interviews employees at 12 companies, and then, based on the results of the interview, gives each company an employee satisfaction score. So the unit of analysis here is a company, and this independent firm is deciding what the employee satisfaction is like within that company. Now, some of these companies have put an employee feedback system in place as a means for employees to communicate concerns to management. So the primary question here is whether companies with such systems have higher satisfaction scores than those without such systems. And we're going to hypothesize that they do. Here are our hypothetical scores for the 12 companies. EFS represents those companies with an employee feedback system. No EFS, of course, means they do not have an employee feedback system. Here are the null and alternative hypotheses. The null is that the median for the employee feedback system, or EFS, is equal to the median for no EFS. The alternative is that the median is going to be higher for EFS than the median for no EFS. Now, if the null hypothesis is true, the two types of companies share the same median. So to estimate this common median, we can combine all the scores. So that's what I've done here. In this first line, I've taken the EFS scores and no EFS and created an all companies vector, so it's all the scores, and then I find the median of all companies. Remember, we're doing this because we're doing this under the null hypothesis, and if the null hypothesis is true, that there's no difference in medians, then the best estimate that we can get for the median is to combine all the observations that we have. Note that we knew in advance how many scores would be above and below the median. Why? Because it's the median. And so we know that of those numbers of scores, of which back here we had, looking at this, 12 scores, we know that 6 are going to be above the median and 6 are going to be below the median. So we create a little matrix here. If we go back and look at our data, remember that the median is 7.5. We notice that 1, 2, 3, 4, 5, 6 are above the median for the EFS. And without even counting, I can tell you that none of them are above the median for no EFS. How do I know that? Because I know that 6 have to be above the median because we have 12 scores. So you can see here in our matrix how we set it up. The number of successes, that is, how many above the median in one group is 6, in the other group is 0. The number below the median is 1 in one group and 5 in the other. Remember that these were not equal sample sizes. We had more companies in the EFS condition, which is why we're able to get this type of data. Fisher's exact test provides a p-value of 0.00756. So in fact, we can reject the null hypothesis. And if we want to dig a little bit deeper with this, beyond looking at the differences in our proportions above and below the median, we can also look at the odds ratio. And we see from the 95% confidence interval that the odds of being above the median, if you're in an EFS company, are about 2.5 times greater than the odds of being above the median if you're not in an EFS company, and that's at least 2.5. This confidence interval goes from 2.5 to infinity. It's a very wide interval. Now let's look at a large sample approximation. We're going to redo the study, but this time assume that we observe 200 employees. We're going to do a two-sided test. In fact, I have set it up here so that we have 100 employees from EFS companies and 100 employees from no EFS companies. We know, therefore, that there's going to be 100 above the median and 100 below the median. 58 of the 100 that are above the median come from the EFS company, and 42 of the 100 above the median come from the no EFS company. When we run the exact test, we get a p-value of 0.03364. Note that if I use the chi-square test with the exact same table, I get a very close result, 0.03389. That is, the chi-square test is a large sample approximation for Fisher's exact test. Now, if you sit and think about that a moment, you might wonder how that could be. The chi-square test was a large sample approximation for the product binomial in which we had complete independence. And now with the hypergeometric, we have some dependence. So how can the chi-square be the approximation for both? The reason is because the larger the sample you have, the less dependence you have among the observations. In this case, where we have 200 employees, it's only when you have entered most of those 200 observations when you start to know what the other outcomes are going to be. So therefore, we have reduced dependency with larger samples. And that is why the chi-square test can give us approximate results. Here are some considerations when working with 2x2 tables. The number of fixed margins determines whether the sampling distribution is product binomial or hypergeometric. For the product binomial, we have one fixed margin, that is, we know the sample sizes in advance. For the hypergeometric, we have two fixed margins. We not only know the sample sizes, we know the number of successes in advance. The two-sample median test is a special case of the Fisher-Irwin test because median 1 equals median 2 implies that delta equals 0. So even though we introduced the Fisher-Irwin test as a test for delta, when you have quantitative data and you're looking at above and below the median, you can look at the proportion above the median for each of the two samples to obtain a delta, and in the population, delta equals 0 is equivalent to median 1 equals median 2. Even though we're doing a Fisher-Irwin test, or what is known as a Fisher's exact test, the two-sample median test is not quite exact. Why not? Because we had to determine what the population median is through estimation. We combined all the scores to estimate that common median. So it's not really an exact test, but it should be close. If the response variable is quantitative, an assumption of symmetry provides a test of mean equality. That is, if we assume that the distributions for the two samples are each symmetrical, then we can do a test of the mean that is a competitor to the t-test without needing to know that they're normally distributed, just that they're symmetrically distributed. That's because the mean and the median are going to be equal with symmetry. The product binomial and the Fisher-Irwin test, as we have seen, are asymptotically equivalent. That is, the test statistic for each of these approaches a distribution that's approximately a chi-square.